Oops, sorry. Let me first of all thank everybody for Christy and Sape for inviting me to come here. It's a tremendous honor to participate in this wonderful occasion where Varadhan received the Abel Prize. I go back. It just reminded me of the talk that he gave. It took me back to the late 60s and early 70s to the Courant Insitute. I got there in 1965 as a graduate student. As he said himself, he arrived in 63 as a what today it's called a postdoctoral visitor. And you may wonder what the graduate students thought of young assistant professor Varadhan at the time, the late 60s. Of course, everybody was in awe of him, a brilliant young guy. Very confident. You wouldn't, he never had any doubt about where he wanted to go and what he wanted to do. And in the early years, I didn't quite mesh with him. We got to work together a little bit and then a lot more in the early 70s. So what I wanted to do today is talk about the work of Varadhan on homogenization. I'll tell you what that is in a few minutes. Which he didn't mention. It is connected to large deviations somewhat, but it kind of started in the early 70s, and I will give a little bit of history of that. Then I want to explain the origins of the problem in spatial averaging. Then homogenization in periodic media, which started, say a little bit about its origin. Then that's the part that Varadhan got interested in, homogenization and diffusions in random media. That's about the mid-70s. And I want to point out what the problem looked like at the time, what was mysterious and what actually got solved. And I won't spend much time in intervening years how the subject evolved. I want to jump to the present, to some of the things that he's continuing to do with his students on the Hamilton-Jacobi Equation in random media, which is a fascinating subject with considerable complexity, which is only now being unraveled. And I will skip the last one. I mentioned it here, but I'm not the right person to talk about it. I haven't thought about these hydrodynamic limits in many years, and Raghu and his students have pushed the subject so far today. I think maybe Yao should have been the person to talk about this. That would take a long time to do justice to all this work on hydrodynamic limits. So let me begin with spatial averaging and explain what the problem is and where it came from. So the problem is we are dealing with partial differential equations that have very, very rough in the sense of oscillations up and down in their coefficients. So you have a diffusivity, A of x, as a function of x. It oscillates. It doesn't have to be periodic. It could be random. We will see in a few minutes. And you look at the this elliptic equation with an inhomogeneous term on the right-hand side, f of x. X is in some domain, some very general domain, bounded or not, in RD, with Dirichlet boundary conditions. And the question arises, what happens if A of x varies rapidly with respect to x? In other words, if over a typical domain D, over this domain D, A of x oscillates many, many times, takes different values, but with high frequency, spatial frequency. What happens? And you might conjecture, and of course it had been conjectured that and had been worked out in physics literature that the solution of this equation U of x should behave like the solution U bar of another equation in which the coefficients are constants. This A of A super H is some homogenized or effective coefficients which should depend neither on the domain D nor on the inhomogeneity that drives the equation, the f of x. And the question is there really such an approximation? And if so, how is the A super H to be computed? And what is it really? So that was the question. This question goes back many years. In periodic media, I'll say a little bit about the history. It goes at least into the middle of the 19th century. Lord Rayleigh was interested in it. Many of the mathematical physicists, what we call today mathematical physicists at the time, were doing. Maxwell was interested in this, where you have either in electromagnetic problems or in hydrodynamic problems or in any number of physical problems where you're not quite at the molecular level. You're interested in replacing a very complex medium by something that has its average properties. And by using these average properties of the medium, you can calculate correctly macroscopic effects. And the word mesoscopic physics comes in, or mesoscopic structures, to distinguish from the word microscopic that refers to molecular level or submolecular level things in which the partial differential equation itself may not be valid. In other words, the idea is that here we're passing from one equation to another equation. Here I'm still at the mesoscopic level. I'm still dealing with a partial differential equation, whereas if I had gone to a molecular level, I would be down to some other, maybe quantum mechanics, some much more complicated level. I'm not going into that far down. So the history of this problem, as far as mathematicians are concerned, begins with these periodic structures in the early 70s. There was the first paper. I didn't put it here on the slide, but I will tell you what it is. There was the first paper that really addressed this question of a limit at the differential equations level was at the pure mathematics level. It was a paper by De Giorgi and Spagnolo, which appeared in two analysts, which appeared in 1973, in which they studied they called it, they introduced the theory of G convergence, in which they studied equations like this, like this one right here, with the A of x periodic and uniformly elliptic, with A of x bounded above and below uniformly. And then they asked, this convergence, the convergence in L2 of the solution U to something, they called it G convergence for Green's function convergence, because here it's the solution that converges. We're not concerned about the coefficients, and we're not concerned about the f. Of course, the coefficients what they did assume is that the coefficients depend on a parameter. If I have it on the next slide, yeah. The coefficients now were periodic. They were rescaled to depend on a parameter epsilon that measures the relative size of the period of the oscillation to the size of the domain. It's a dimensionless parameter, so when epsilon becomes smaller and smaller, the oscillation of A increases. So this A of x over epsilon does not converge strongly in any sense. It only converges weakly because the oscillations cannot possibly converge pointwise. And so the convergence of U, epsilon, the scaled solution, to something, they called it G convergence. And they proved a theorem that says that U epsilon converges in L2 to something, and that something was an equation with not quite constant coefficients, because they didn't actually do this periodic case except as an example towards the end of their paper. But they basically guessed, or they had a theorem out of which you could extract what I'm suggesting here. At the same time, in 1973, Sanchez Palencia at the University of Paris 6, who was a professor of mechanics there, had this idea that he knew the result of the Georgian Spagnolo, and he wanted to apply it to problems in mechanics. And he tried to approach the problem in a more computational way and try to find out what the AH was. He tried to be a little bit more precise about what the A super H should be. And then I was, in the fall of 1974, I was visiting in France, and I was in close collaboration with Ben-Shusan and Lyons at the time, and we figured out how to carry this asymptotic result using correctors. In other words, using the first order approximation, asymptotic approximation of the solution, and creating test functions and so on, developing a theory that produced the asymptotic limit in a systematic way. And almost at about the same time, Raghu and I were in parallel following the probabilistic version of all this. Raghu didn't mention that during the period that he was working on large deviations in the late 60s, he also started at that time to work on the martingale formulation of diffusions, a very elegant, weak formulation for the definition and characterization of diffusion processes in terms of martingale problems, completely independently of or in parallel with the work he was doing on large deviations. And the question was, could this homogenization theory or its probabilistic versions be put into the framework of the martingale problem and carried out there? The martingale problem, one of the most interesting applications of the martingale formulation of diffusions was that asymptotic analysis, limit theorems, could be proved very elegantly in that framework. And in fact, Dan Struck and Raghu had, at the time, in their early papers on martingale problem, they had theorems within the martingale context in which they looked at elliptic equations or diffusions in which the coefficients A epsilon, here A, or A epsilon, were perturbed, and they were converging to another. If the coefficients of the operator converge, will the corresponding probability laws of the diffusion processes converge? But they were restricting themselves to a strong form of convergence in the coefficients, and so the homogenization part, which involved this weak convergence, in other words, the coefficients converge weakly, but the processes converge in a stronger form. They converge weakly as processes, but that's in terms of elliptic equations, it's this Green's function convergence that I was talking about. So this is how we started working on the problem. This is around 1974. It is about a year after that summer of 73 that Raghu mentioned that Donsker asked him the question about how the Feynman-Katz, the asymptotics of the Feynman-Katz formula for large time could be related to a large deviations problem. I remember that summer very well because Donsker was asking, he didn't only ask the question to Raghu. Raghu actually solved the problem, but he was asking the question to everybody. And so I recall that summer, yeah. I was in Europe that summer. I got back and I saw Raghu. I was thinking about it. It didn't occur to me that you should use the occupation time measure that Raghu mentioned. Neither did Dan Struck. We were both talking about it. We thought Donsker wasn't quite, he was asking the wrong question. But Raghu realized, no, it wasn't the wrong question. It was the right question. He found a solution to it. Raghu came back. He was in India that summer. And he was very refreshed. He had not, I asked him, how was it? He said, well, I had a good time. I didn't do anything. His mother cooked his favorite dishes for him. And so he was in this state of being highly refreshed that he solved that problem very elegantly. And well, of course, in parallel, he was doing many other things. He was into these martingale problems, and that's when we started working on this probabilistic form of homogenization. So in the mid-70s, then the question arose, what if the coefficients A of x were not periodic, but they were random? And that is really an extremely interesting question. We had no idea what to expect. It's a very interesting question to reflect back what the state was then, before we actually, now of course we know very well what the answer is. But the reason that the problem was puzzling at the time is because there is no separation of scales. Let me say what that means. The problem here is a little bit deeper. We're really talking about, it's a multi-scale phenomenon. We have a differential equation in which, or a differential equation that models a phenomenon that occurs on many scales. The coefficients vary on one scale, the solution varies on another scale, or on several different scales. And when you go to the random case and you ask, what if the coefficients are random, a stationary random process? Here's what a stationary random process looks like. It is a function of x and omega. Omega is in a probability space. And this function can be written as the translate of some other function, a tilde. A tilde is a function on omega. It's a real valued function omega. It actually could be a matrix, but let's say it's a real valued function that is strictly positive, a tilde of omega. And now you take this function and you translate it. You assume that you have a group of translations, tau sub x. X is parameterized by a point in Rd. And these are transformations of the space omega, the probability space omega, into itself. And they form a group. And they preserve the probability measure P in this sense. And they're also ergodic, which means that the only sets that the sets that are invariant with respect to translation have probability 0 or 1. So if you make just that assumption, you say that a of x and omega, the coefficients in the equation, have just this property. Do you still have G convergence, if you wish, in the Giorgi-Spagnolo sense, or do you have a homogenization result? Do you have a convergence to a problem? Does the solution of the problem with random coefficients, this problem here, the solution of the equation with random coefficients, which now itself depends on omega, does it converge to something that has constant coefficients? And now the separation of scales is gone. There's an epsilon in the equation. I forgot to put here, this should have been a epsilon. In other words, you should speed it up. Instead of having a of x and omega, you should have been a of x over epsilon, comma omega. So you speed it up, but it doesn't mean anything, because this A, this random process A, is not periodic. It has characteristic scales of every type. If the region D, let's say, it has approximate periods, if you wish, or it has if you look at the spectral representation of this process, it contains frequencies arbitrarily close to 0, which means that it varies on scales that are arbitrarily large. So for whatever domain D you have, and for however small the epsilon is, there will be scales comparable to the region itself. There is no strict separation of scales. So we were wondering, if that is the case, can there possibly be a homogenization result? And we didn't know. We didn't know this. Nobody in France, I wasn't coming and going to France at the time, nobody in France really, French being mostly analysts at this time, not yet probabilists were involved. And so it was a very interesting surprise, actually, that in 1977, the paper got published in 78, we did prove this result, which says that the solution u epsilon of this random elliptic equation converges to a deterministic one, u bar, in this mean square sense, like that. In other words, when you take the difference, you square, you integrate over the domain, and then you take the expectation that the limit goes to 0. And a large part of the problem was to find out what exactly is the cell problem. What exactly, how do you, I I should have mentioned a little bit earlier that in a periodic case, let's go back for a minute to the periodic case. In a periodic case, what you have is, in retrospect, the periodic problem is very naive. What is it saying? Periodic homogenization says something very simple. If the coefficients oscillate on a small scale, then it should be possible, as the separation of scales increases between the period and the size of the domain, that increases, becomes extreme, the original problem should decouple into two separate problems. It should decouple into how do you calculate locally on a period cell the effective coefficients, and then having calculated the effective coefficients, how do you find the macroscopic behavior by solving the homogenization problem? In other words, how do you solve, if this is the original problem here, then asymptotically, as the separation of scales is exaggerated, then this complicated problem simplifies, reduces into two very distinct problems. A local problem for the coefficients and a global problem with constant coefficients for the solution, U bar. And the exact same thing happens in the random case without any hypothesis whatsoever on the coefficients, A, except the ellipticity and the ergodicity. It's a striking result when you think about it. From that, today it's not striking at all, but well, it still puzzles people because people get. I will tell you what puzzles people today. They see the x over epsilon here, which unfortunately I forgot to put the epsilon there. They see the epsilon and they think that in the random case there is a residual separation of scales. They don't quite grasp the fact that there is no separation of scales here. Why is that important? It's important because it has enormous implications for the computations of this, for the actual practical implementation of this result. I'll come back to that point a little bit later. So, in the random case, how does this idea of local-global, this asymptotic decomposition, how does it get realized? Well, the result becomes very simple. It says that there's the cell problem becomes an abstract cell problem. In other words, I have some chalk here. The solution is a function u epsilon of x and omega. The coefficients are some functions a of x over epsilon omega, which is in the form of that translates tau x over epsilon acting on omega like that. But the solution, this is what stationarity means, that this function a can be represented like this. The u epsilon, this solution is not of the form, is not of course of the form, it's not of the form some other function, capital U, let's say, of tau x over epsilon omega. It's not of this form. It depends explicitly on x also. It is a form, it is like that, but it depends on x as well. And the idea is, what the asymptotic theory tells you is that, yes, the solution of the full problem is complicated. It depends on the translates with respect to omega, but it also depends on x. And asymptotically, the two decouple. This part goes with the cell problem, the coefficients, and this part goes with the solution of the homogenized problem, the U bar. It says something very intuitive. There is this just complete separation, the global problem for the U bar, and the local problem, which is not very local now because it's an abstract cell problem. The cell is not a small thing; it's the whole space. And but the tasks are separated, strictly speaking. So that's what homogenization in random media was. Where is homogenization theory today? Let's jump forward. A lot of things happened in between, as you can imagine. By the way, I should mention that right at about the same time, 77, 78, the paper was published in 78, but the work was done the year before, Sergei Kozlov had solved this problem in a very similar way. And later on, he visited us in 1984. He visited us in New York, and we came to know him a little bit better. He was a very smart person. He died relatively young a few years ago. But he has done some extremely interesting work in homogenization, and we followed his work. Raghu and I followed his work closely at that time, after we realized that he had done that. Now, is it always true that when you have an equation with random coefficients, this extremely fortuitous thing will happen that we have a result, let's say, where the coefficients are periodically vary in a periodic way, and then you go from periodic to random, and miraculously the results carry over as if there was no difference, even though there's a huge difference between the problems. Well, of course, we lucked out. This doesn't always happen. It happened here. It happened in this problem here, but it doesn't always happen. So what is it that made this problem such a perfect theorem with absolutely no hypothesis other than stationarity that you get it? And what it is we realized very quickly is that there are some structural properties that are absolutely essential for this perfect theorem situation to occur, and that most of the time they don't occur. So what it is that there are some structural properties that underlie this. Is some structural properties that, from the probabilistic point of view, say that the corresponding stochastic process is very well centered. It has some time reversibility properties. From the PD point of view, it says that the equations are in divergence form, whether or not the coefficients A or Aij are symmetric or not. And whether or not you have a variational characterization. Those are things that play a huge role in this problem, and that's where a lot of the work in the last 25 years or so, 30 years, has gone, is in unraveling case by case or in individual situations what can happen. And there are still unsolved problems here, plenty of unsolved problems, even for these basic elliptic equations, when, for example, when you have random drifts, the situation is much more complicated when the drifts don't have all the right properties. They don't, for example, they're not divergence free, or they're not curl free, or they're very general in some ways. Then we have results, of course, but they're not anywhere near as clean as this kind of homogenization. And methodologically, everything relies on the correctors. Everything relies on these auxiliary constructions that make this separation, this exaggerate the separations or exploit the separation of scales, that tell you that this function can be written essentially as a function of x and as a function of tau x over epsilon omega. It's an ansatz that realizes this idea, almost, not quite. That's the corrector construction. Does that always work? Well, here's a very interesting situation that got only explained recently. That is in connection with the Hamilton-Jacobi equation, which is, I have written it here, is in backward form. This is a typical backward diffusion equation with a nonlinear term, in which the nonlinearity is in the first derivative, the gradient here. And here h of x p, here's where the gradient goes in omega. This function is some function of the form, it's a translate in omega and p. So it's stationary in x with respect to omega. It's a stationary process in x for fixed p. So when the h is like that, and you have a random Hamilton-Jacobi, and it is convex in p, and it is convex in this variable. If you have such a partial differential equation with a terminal condition that is a nice given function f of x, and let's say in all of our D, no boundary conditions, do you have a homogenization result? If you put the epsilons in and you do the epsilon asymptotics, do you have a result like that? Well, the story for that problem is very interesting because in the early 80s, Pierre-Louis Lyons, he was just a I had to say that Pierre-Louis Lyons was a fresh PhD at the time because he had already, I don't know how many papers, he had already done a lot of work. But he was visiting at Courant, and we sat in one afternoon together with Raghu, and it was very easy to figure out how to do the correctors for this problem, how to write correctors in the periodic case. So the periodic Hamilton-Jacobi equation, where the coefficients here, periodic functions, by the way, can be written in this form because in the periodic case, the space omega is just a torus. And the translation, tau x omega, is a point on the torus. That's the periodic case. And tau x of omega is just omega plus x, is ordinary translation, modulo the torus. So in that case, you could write down correctors, and we put together a paper. This paper got never published. It's cited all the time. The younger generation discovered this paper, and they're fascinated because they keep citing it because it's an unpublished paper. It has a certain cachet attached to it. And the reason the paper never got published is because we parted. He went back to France and said, okay, let's work on a random problem. And that random problem, turns out, is an impossible problem. There are no correctors for it. It's very hard to construct correctors for the Hamilton-Jacobi equation in the random case. And only very recently the problem was solved. Pierre-Louis Lyons got back into it again with Souganidis, and Raghu and his students, former student Rezan Kanlu and Kosigina, they wrote very recently a series of papers, not using correctors, but exploiting the variational form of the Hamilton-Jacobi equation. It's a very interesting development. It's a very interesting papers where they exploit the fact that U has a variational characterization, is the value function of an optimization problem. In what I'm going to say in a few minutes, it comes up again. You will see what I mean by that. So the variational form was used, and there are no correctors. So this is a methodological interesting situation. That's where, from the theoretical side, from the ergodic theory, this underlying here that's what interested Raghu, is he saw that in this problem there's a very unusual and exciting form of a new type of ergodic theory that is taking place. Kind of a nonlinear ergodic theory that you have nonlinear functionals of translation invariant functions, which is what the solutions of the PDE are, and there's an ergodic theorem for them. The limit of these things becomes deterministic, becomes a function of x only, the averaging. What about from the, averaging and this kind of homogenization theory is of broad interest in science. It's not just some probabilists who see the ergodic theory behind this and focus on it. What about the general problem? What's the status of that? Well, here's where the problem stands today, I think. One very interesting issue is how do you find properties of AH? AH, the homogenized coefficients, are uncomputable, except for one-dimensional problems and some very, very special two-dimensional problems, very, very simple special problems where there's some symmetry that is helping you. You can never compute the A of H. So therefore, you want qualitative properties of it. You want bounds. In general, it's a matrix. So you need to do something. You got to find bounds, and it's a fascinating theory behind this. The variational form is used. It's an entirely different subject. It's not so much of interest to probabilists. So the probabilists haven't done very much with it, but there is one person that has done a great deal with it, and that's Graham Milton. He was at the Courant Institute in the 80s. That's where he did most of his work. He's a brilliant guy. He's now at the University of Utah. And he's continuing to work in this area. Another question, which is dominant today, is how do you, from the computational side, from the point of view of, let's say, numerical analysis, although it's larger scientific computing, how do you compute multi-scale problems? When you have problems with coefficients that depend on many scales, what are effective computational methods? What are good computational methods? And the key here is to find computational methods, find adaptive meaning where the numerical method kind of searches to find what's the right way to advance without you telling the method in advance what to do. How do you find adaptive finite element methods or other methods, schemes rather, that capture homogenization? That homogenization may or may not be in the picture, but if there is homogenization to be had for these problems, do the numerical methods capture it correctly? That's a great question. It's still, recently there has been some progress in it. About 10 years ago, Tom Howe, who also was at the Courant Institute in the late 80s, has done some very nice work in this area. I think it's a fascinating question. There's a lot more to be done there. I'm getting back into it. I think people push me in this area because they ask so many interesting questions. Another one is, how do you deal with nonlinear partial differential equations in which the multiscale problems are generated intrinsically? In other words, you do not put in the multiscale structure or the physics of the multiscale character of the coefficients is not there because of you're in some environment or another, but the very nonlinearity of the evolution generates the many scales. That's a very interesting problem, again, that people in material science deal with primarily by variational methods. And some of the corrector type calculations that have been developed for usual homogenization carry over, or at least can be extended to these methods. Finally, I mentioned that there is also a deeper probabilistic question. These are the questions I've been discussing right now didn't have much to do with a randomness. But here's another one, and that is, it's coming up now, it's very fashionable, this question, is how do you compute numerically the whole probability law of this? In other words, people ask, computers being what they are today, it's an entirely different situation. Back 30 years ago, we really wanted to approximate this by a constant equation. Now, people, I don't know, they have terabytes of operations or huge computers, parallel computers, what have you. They really want to calculate this as a function of x and omega. And what's a good way to do that? And, of course, what is a good way to do it that captures correctly the multiscale behavior? In other words, what's a good way to do it that is consistent with this asymptotic limit? That's the interesting question. And that requires some new ideas, I think. It's multiscale sampling algorithms. It's an entirely new and very interesting subject. It's one of these situations where, again, probabilists are kind of in the margin of all this. It's other fields, some numerical analysts, even engineers are jumping into this, and probabilists haven't quite become conscious of the fact that there's some really interesting questions lurking there. Okay, now I'm going to go to my second half. I think I'm running, it's not half, it's maybe, how much time do I have?
Another over 20 minutes.
Okay, so the last 20 minutes, I want to talk about a subject that has always been in Raghu's mind, and I thought I'd present something about that, because all the years I was at Courant, I was there until I got there as a student in 63, and then in 65, and then I stayed as a faculty member, and I left in 93 for Stanford. I still don't know why I did that, but all my friends are at Courant. So Varadhan was always very much interested in financial math. And just to put this, it was kind of an arrogant attitude at Courant regarding, in the 70s and 80s, regarding financial math, that we were doing more important things than what financial math was carrying out at the time. And who would ever doubt that what Raghu did wasn't infinitely more important than what financial math people were doing? But it turns out it was happening at the same time too. The Black-Scholes paper was published in 1973. There's a very interesting paper of the theory of options pricing, the Black-Scholes theory of risk-neutral pricing, materialized around there in the early 70s. Merton claims that already in 69, 70, he was teaching it and he was aware of this. Merton was a student of Samuelson at the time. And Samuelson in 1973 gave the von Neumann lecture at the SIAM annual meeting on this theory of options pricing. And he has a very interesting article that appeared in 1973, which I find fascinating reading, because he kind of runs historically through the evolution of his own thinking about pricing of options. And then he's not quite sure how the options should be priced. What exactly should it be priced relative to the speculator, relative to whoever is issuing the contract, the options contract, and so on. So it was 1973 that the Black-Scholes paper came out. 1974, the Chicago Board of Options Exchange was established. So options were very new in the mid-70s. I read that paper in 1973. I don't recall, I don't think I heard a lecture by Samuelson. I would have remembered it, but I do remember reading that paper. And it turned me off. I'll be absolutely honest with you. I read that paper and I said, why are they getting excited about it? It's just a lousy heat equation they're solving. We have a lot more interesting problems to do here. Of course, I changed my mind. That there were a lot of interesting things that they were doing. And here is 30 years later, 30-some years later, something phenomenal has happened. Financial mathematics has embraced stochastic analysis as its homonist language. I mean, if you look at financial mathematics today, there are young people, there are young mathematicians that have studied financial math from our courses. They have learned it from the books that have come out. They do not realize that stochastic calculus and the stochastic analysis did not exist except to serve financial mathematics. They have no idea that that was the case. Ito's formula is people discuss it over the phone. Sometimes students have to interview for jobs over the phone, and they're being asked, what is Ito's formula? Ito's formula, over the phone. And they have to explain it. So something dramatic has happened. It didn't have to happen this way. It didn't have to happen. I mean, physicists, if you go into the physics literature, you rarely encounter stochastic analysis as we know it. Rarely. The physicists it's completely off their radar screen. They're not interested in it. How did it happen that this rather sophisticated mathematical theory, very nicely developed and so on, how did it happen that it was so immediately absorbed by this new field? Well, some credit goes to Merton because he's the first one to realize he's the prophet who brought stochastic Ito's formula to the financial world. But a lot should be said in recent years for the probability community, who has taken up very diligently the analysis of these problems. There's an explosive interest in financial mathematics among younger mathematicians today. And it's not only, people who cynically would say it's because there are jobs out there in the banking industry. It's not that at all, I don't think so. Of course, there's some of it. But you find some extremely good students. Some of our best students are attracted to these problems. And you can't explain that in terms of jobs. And I have no doubt, I've become really convinced, sometimes I talk like a convert, that financial mathematics has kind of overtaken probability in some ways, and it's really driving research in probability in a very interesting ways, creating questions and things that we wouldn't normally have been looking at. So having given you this long preamble, let me show you an example of what you can do in financial math. Here's the question I'm asking. It's a very simple question. Do investors that are portfolio optimizers influence the market in some way that is different from that of standard reference traders. Let me tell you what that question means. When you trade, when you buy and sell stocks in equities from wherever, does it affect the equities market? Does it affect the price of the very thing that you buy and sell? Of course, it does a little bit, but it kind of, in a stable equilibrium case, no one individual transaction changes how the prices themselves vary. That's the principle that we all agree, that there are, for whoever, as many people as are interested in buying something, there are as many people who want to sell. But now, you ask the question, what about people who are more intelligent? They are portfolio optimizers. There are people who are not just buying and selling, speculating on the price of something, but who are systematically building portfolios where they rebalance their holdings between risky assets and riskless assets in such a way as to come after a certain time to come up with a portfolio that has a high value, high utility. Do they have an influence on prices because they act in a more organized, more systematic way? Now, this question is interesting because of the related question, which is a little bit scarier if you ask it in a slightly different way, is do traders that maintain hedging portfolios influence the market in a particular way? That question is interesting. It says, when options and other secondary instruments, contracts, are being issued, the very maintenance of these contracts requires creating hedging portfolios, creating portfolios of risky and riskless assets that are dynamically adjusted to replicate the price of the instrument that you have sold so as to diversify the risk in holding or selling that instrument to somebody. That is the fundamental principle of risk-neutral pricing, the possibility of also hedging these instruments. So now you have traders who do nothing but trading because they want to maintain their hedging portfolios. Do they influence the markets? Do they change the very prices of the things that they're trading? Well, that's an interesting question, and if you remember in October 1987, the S&P 500 Standard & Poor's Index dropped 22% in one day, which was one of the largest. I think it probably was the largest one-day loss. It was larger than the 1929 loss for one day. The markets recovered afterwards, but at the time, people were convinced that it was program trading. The words program trading are kind of tied with October of 87, because they thought that the people who were the hedgers, they had created additional volatility in the markets that created the crash. So therefore, if you wish, this very unusual event, this large deviation in the markets, the crash of October 1987, was precipitated by program traders who trade because they want to hedge their portfolios. To hedge their portfolios, the dynamically adjusted portfolios that replicate options. Another way of saying it is that hedgers increase the volatility of markets. They may not make the prices go up and down, but they increase the volatility. Well, what about portfolio optimizers? So, first of all, a little bit of history. The effect of hedgers or program traders has been of interest. I've already mentioned that since 1987. Theoretical studies of that appeared relatively early. Hans Fellmer and Schweitzer studied this in 93, and then there was a sequence of papers. I got involved with this about 10 years ago. And the main result, with a couple of different models, is that program traders do increase the volatility of the underlying asset. This is all model-based. Calibration issues are very hard to come up with. What do I mean by calibration issues? What I mean is that it's very hard to quantify. These are qualitative models. It's very hard to quantify them, although that's a very interesting issue, how one should do that. Now, what about portfolio optimizers? Portfolio optimizers are different from traders. Portfolio optimizers are working for themselves. They want to increase the value of their portfolios. And the answer is, that's what I want to explain a little bit now, is the answer is that portfolio optimizers are good for markets because they bring down the volatility. And the question is, why do they tend to decrease the volatility? Now, there's a very simple explanation for that. So let me first, before I give you show you the model that gives you that, let me explain why this happens. When you're a portfolio optimizer, you focus on how much you should hold, how much of the risky asset you should hold, and how much of the riskless asset you should hold. And one of the most fundamental principles of portfolio optimization is rebalancing. In other words, when the risky assets, their value increases, then the relative proportion of the risky assets in your portfolio increases. And if you're going to maintain the proportion constant, you have to sell. So in other words, if your portfolio is gaining in value because the market is going up, you should be selling in order to maintain the correct proportion in your portfolio. Well, that means that when the markets are going up, you should be selling the very stock that is appreciating in value and putting your money into a riskless asset. Well, that clearly brings the volatility down because you're selling when the market is going up. That's the very opposite of what program traders are doing, the hedgers, because they, in order to replicate the price of an option, when the risky asset price is going up, they have to buy more of it in order to maintain the replication property. So they increase the volatility. Well, that's the simple answer of why these phenomena are occurring. Let's see how to model that mathematically. And so the analytical model is very simple. You have to, here's what the elements of the model behind it. You assume that there is an incomes process that together with an incomes process means that people invest because they have money to spend. So the incomes process might be the GDP of a country or some other macroscopic variable that counts the prosperity of a class of investors. So you have to put that in, that people have some prosperity in order to be able to invest. And then you have this incomes process together with the underlying price of the risky asset, which underlying price of the risky asset is influenced by the overall prosperity. So you have to put that into the picture. Then you have to put in what portfolio optimization means. Portfolio optimization means that you hold a risky asset and you hold a risk-free asset, and you maximize an expected utility of your overall wealth at a target time horizon. And then there is a clearance constraint that the risky asset price process adjusts so as to satisfy the demand both of reference traders and of portfolio optimizers. In other words, there's a finite number of risky asset. The total value of the risky assets out there is fixed, and you, the portfolio optimizer, are competing with everybody else who is buying and selling in that market. So the prices are limited by the total availability of risky asset. If you cannot buy indefinitely at a constant price, eventually the price will rise. So mathematically, what this says is that it couples the evolution of an asset price process to a wealth process through a Hamilton-Jacobi equation for the value of the wealth and a clearing condition that balances the demand for the risky asset. So here's what I have a few equations to explain this, and then I will show you some figures of what happens. So you have this aggregate incomes process that is, let's say, it could be geometric Brownian motions. Normally we take it as geometric Brownian motion. I did not put here separation of scales. I did not put time scales. The averaging and homogenization issues that are behind this are fascinating. They haven't been worked out. That's one reason I'm talking about this here, is because things are not happening in as simple a way as I'm describing. The aggregate incomes process is varying much more slowly than the price process. Well, I'm not taking that into consideration here, but I could if I were to put these averaging ideas into play. So here the risky asset price, though, is varying in a way that is complicated because the alpha, the mean return, and the volatility sigma are not known. The alpha and the sigma have to be determined, the coefficients. It's a highly nonlinear situation. The riskless asset is given with some fixed interest rate R that is out there. But now that we have demand functions, that the demand of the reference traders, the demand for assets, for risky assets, is a function of the price and of the overall aggregate incomes process. Think of it as the GDP. And then this has to have some homogeneity properties, which are eventually become something very simple. I won't go into that. There are some very simple reasons why these are good choices here. This is the wealth process. This tells you how the wealth of the portfolio holder, how it changes. The wealth W, this is the value of your portfolio, in which you hold pi of the risky asset. Pi W is the amount, the fraction, the total amount in your portfolio in the risky asset. Pi is the fraction, W is the total portfolio value. So this is what is changing in a volatile way with this Brownian motion. And here is the growth alpha of this is the growth alpha pi W that is for the risky asset, and then 1 minus pi R times W is the growth times R times W is the growth of the riskless asset. So it's all part of the drift here. And now here I'm assuming self-financing in order to write this balancing equation. And then the value function, if you look at the supremum over all allocations, you look for what is the optimal allocation in your portfolio for the expected utility, U is the utility function, of your wealth at terminal time capital T, then this satisfies this Hamilton-Jacobi-Bellman equation. A very simple equation to derive. It's notice that it's highly nonlinear because you take the supremum pointwise of pi over here. And to connect with averaging and homogenization, if I had taken care to put in here the variable time scales, this would be a much more complicated, the difference in the time scales, this would be a much more complicated equation. But remember that here the alpha and the sigma are themselves not known yet. The alpha and the sigma are not known yet, and of course I also have the clearing condition. So in order to simplify the problem, I first assume, I say, what if there was decoupling? What if it was just a pure, perfect portfolio optimization, the prices were never affected? Well, that's a very simple case. If the utility is just a simple function here, this kind of, it has a name, it escapes me right now, I don't remember it at the moment, but this very simple utility function with lambda, it's a concave function, lambda less than 1, does not equal to 1. In that case, there's the optimal, this is a standard problem was solved by Merton in 74. These were the problems that were being solved in the mid-70s, and they looked so simple to probabilists at the time. Is an explicit formula that tells you that the optimal allocation ratio, it's a very simple function of the excess return. Alpha 0 is the return when there is no coupling. Alpha 0 is a constant. When there is no coupling, there's no change in the prices, minus the interest rate divided by the volatility when there's no coupling. This is the demand of the portfolio optimizers, which can assume it is proportional, it's equal to the relative holding of the risky asset. This is the amount of pi W is the amount of risky asset that you're holding divided by the price of the risky asset. This is the number of risky asset shares that you're holding. And now your demand is going to be this function. So then the clearing condition that couples everything is this is the demand of the reference traders. This is the demand of the portfolio optimizers. This depends on their wealth and the price. This depends on the aggregate incomes and the price. This has to be equal to the number of shares. By the way, when you think of portfolio optimizers, don't think of individuals, don't think of people. Think of pension funds. Think of of large macroscopic entities, hedge funds, for example. And you might say in a market today, what percent could you venture a figure? What percent of the total of the people who trade in equities, what fraction of them are actually portfolio optimizers? In other words, how much money out there that is being invested is invested by pension funds and hedge funds and entities like this that tend to optimize. A good, in the US, you could give a figure around 10% because there are, maybe the total equities are about 120% of the GDP of the United States, about between 15 and 20 trillion dollars, the total value of the equities. And the total value of the hedge funds right now is between 1 and 2 trillion, depending on how you count. Pension funds should be included in there too. So it's about of the order of 10%. So that is roughly the breakdown between who is trading in a random way and who is trading to optimize portfolios. In other words, here you're really asking, what's the effect of hedge funds on the price of markets? And I'm telling you that hedge funds are playing a good role because they're bringing down the volatility. Well, here's what I have here a quick review. I'm going to skip it, and I'm just going to show you this formula. This is a very simple first correction. It says that if you, let's look at this one, the sigma 1. This says that the volatility, if the percentage of people optimizing portfolios is small, and you do a small perturbation analysis, then this is the first correction to the volatility. It says the first correction to the volatility is this formula. It says it's proportional, it's equal to the volatility when there is no interaction. It is proportional to this fraction of the wealth that you're holding in the risky asset divided by the price. And this pi 0 minus 1, which if pi is in the normal range, is a negative number. If pi is a fraction between 0 and 1, it's a negative number. And that's the very effect. That means that the first correction to the volatility is negative, which means that the volatility is coming down. Okay, so it's as simple as that, and then you can solve numerically the full problem, and you can see, I guess you can't see, but if you could see, then you can see that something remarkable happens, and even the horizontal here is the percent of portfolio optimizers. How many? So here's like 20%. 0.2 is 20% of the total trading out there is done by portfolio optimizers. And you can see that the linear theory and the full nonlinear Hamilton-Jacobi theory, they don't differ by much. And even at 30%, they don't differ by much. Okay? I can't read this, but the overall effect is that the nonlinear theory is remarkably close to the simple linearized theory. I don't know why that's the case, but let me end by pointing out some things. Feedback effects can be estimated with simple macro market models. For example, both the effect of hedgers and portfolio optimizers can be assessed. Not only reference traders, but reference traders, hedgers, and portfolio optimizers can all be put into one framework. It's a gigantic, complicated problem, but it can be done. The mathematics, we're talking about relatively simple phenomena, but the mathematics is very interesting and quite complex if you pursue them at a high mathematical level. If you could simplify the problem, go to discrete time, make some simplifying assumptions, it's not a hard problem. It's actually a good problem for young mathematicians to start in. If you put in realistic things, you put in country-to-country variations, if you put in separation of time scales and so on, all of these interesting things that we have been talking about over the years with Raghu come right back in there. And they are potential customers for all these theories of large deviations, the theories of homogenization, and so on. It's an entirely new vista to try these ideas. For example, calculating probabilities of crashes, calculating in these interacting markets to calculate probabilities that some catastrophic event will happen, not just how the volatility will change a little bit. And then another issue, what is really new here, and we haven't the probability community is guilty of not having done anywhere near enough here, is calibration issues. We can't financial mathematics cannot go forever with cute, interesting models that we build and we play with. Sooner or later, we have to come to grips with data. And that's an entirely different ballgame because real data requires a kind of sophistication, a kind of new statistical techniques at a level that just doesn't exist today. Let me give you one last example and I'll stop. Suppose I have this theory, I have these models, I have tested everything. Can I turn this theory around and ask, okay, if I observe the markets, can I estimate using this theory what fraction out there is actually portfolio optimizers? Can I tell from a theory like that, by applying it intelligently, how many people out there, how many institutions, what is the total value that is being traded by portfolio optimizers? That's a very interesting question. I don't know how to do it. I don't think anybody knows how to do it. But those are the kind of questions that we're faced with. And I think that's what makes it a fascinating subject. And I think that it's very much in the spirit of what I call myself the older generation, Raghu and his generation. We are moving away from the center. It's the younger people that are going to take over. Those are the questions that they have to be faced with, and they come up with all these some general concepts and some what are the ways to move forward. Thank you.